So if you're following along, we're currently on page 892, learning about how spontaneity can be calculated through Gibbs free energy using that standard cell potential that we learned about last time. So remember, the standard cell potential, E standard cell, is the what minus the what? Good. The cathode minus the anode is the standard potential of the cathode minus the anode. How can you tell what's the cathode and what's the anode?
Which one's being oxidized or reduced?
Good. Which one's being oxidized and which one's being reduced? So in my galvanic cell right here with the zinc and the copper, which one would be the cathode, the zinc or the copper? So cathode, is that where the reduction occurs or where the oxidation occurs? Reduction occurs, good. So in this example, which one do we say was being reduced, the copper or the zinc? The copper is being reduced, so that's going to be our cathode, which makes zinc our anode, good. And you can look up the cell potentials of the two of them in the table and subtract cathode minus anode to find out what the overall cell potential is of this cell. So we can use that then to calculate whether or not reactions will occur spontaneous by using it to calculate Gibbs free energy using the Faraday constant. And the Faraday constant is 96,500 joules per volt times mole of electrons. So we're going to calculate this as the standard Gibbs free energy is equal to negative n, where n is the number of moles. Now these are moles of electrons, because remember in the Faraday constant here, up here. The Faraday constant is in terms of moles of electrons. So this N right here is going to be moles of electrons, or the number of electrons that were transferred in the redox reaction. When we looked at the zinc and copper redox reaction, there were 2 electrons transferred in that redox reaction that we looked at last time. So for this reaction, N would be 2 moles of electrons. And then F is the Faraday constant, and E standard of the cell, again, is the E standard of the cathode minus the E standard of the anode. And then once we determine what delta G is, how can we determine whether or not the reaction is spontaneous? Good. If G is negative, the reaction is? Good, spontaneous. If G is positive, then the reaction is non-spontaneous. Want to try one of these out? All right. Calculate the standard free energy change, so delta G standard, for the following reaction at 25 degrees Celsius. We have solid gold plus 3 calcium 2 plus in solution, goes back and forth to 2 gold 3 plus in 1 molar solution. The reason why we specify these are 1 molar solutions is because that is one of the requirements of being standard. That little degree symbol that says it's standard state for a solution is 1 molar. For gas is 1 atmosphere, 25 degrees Celsius, etc. Plus 3 calcium solid. So looking at this reaction, the cathode is what's gaining electrons. That would be our calcium ion. Calcium goes from 2 plus charge down to 0 charge. So that is our reduction, which means it will be our cathode. Gold goes from no charge to gold 3 plus. So that is losing electrons, so that is our oxidation, therefore that is our anode. So we need those standard cell potentials, which were on the table 19.1 on page 887, this big table here. If we look up on that table, we'll find that the standard cell potential for calcium to calcium 2 plus is negative 2.87 volts, and gold to gold 3 plus is 1.50 volts. Be careful with transition metals, because transition metals, most of them have more than one possible charge. For example, iron could be iron 3+ or iron 2+. If you're looking on this table, on table 19.1, iron is listed more than one time because it's depending on which charge you're going to. So make sure when you're looking on this table, you're very careful about which particular charge you are looking at, because many of the transition metals are going to be listed more than once on the table and usually not right next to each other, for a big hint there. So make sure you're checking the correct charge when you pull that E standard of the cell.
What page is that?
Page 887. And that's table 19.1. All right. So let's go ahead and calculate E standard of this cell. So that's the cathode minus the anode. So our cathode is going to be which one again? Calcium. Good. So calcium had negative 2.87 volts. Minus our anode, which is going to be the gold, so minus 1.50 volts. So that ends up being what? Good. Negative 4.37 volts is our E standard of the cell. Let me get a blank page here. Just determine the E standard of the cell is negative 4.37 volts. All right, so we're asked to calculate delta G standard. So our formula for delta G standard is negative NF E standard of the cell. So N is the number of electrons that were transferred in this reaction. So looking at the reaction, how many electrons got transferred? 6. Good. 6 electrons. Now, this part right here would not be written for you. So how would you determine just from the top equation that 6 electrons were transferred? Just looking at that top equation, how could you tell that 6 electrons were transferred? Good. So calcium is 2+, so to calcium to 0, that is a gain or loss of electrons. Gain. So it gained 2 electrons, but there's 3 of them. So if I have 3 calciums and all 3 gained 2 electrons, that's how many electrons gained? 6. Double check our math with the oxidation. Gold went from no charge to 3+. That's a loss of how many electrons? 3, but I have 2 golds, therefore 2 times 3 is 6. 6 electrons gained, 6 electrons lost, therefore 6 electrons is the number of electrons that were transferred. So, that color, let's check black. Negative, our N will be 6 electrons. All right, what is F? Good, 96,500. That's the Faraday's constant, and that's in joules per volt. Mole electrons. And then E standard of the cell we just calculated to be negative 4.37 volts. Put all those together and see what we get. As far as units go, moles of electrons cancel with moles of electrons, volts cancel with volts, and the unit we're left with is joules. How many joules? Should be a big number.
2,530,230.
Yep, let's just write that in scientific notation. 2.53 times 10 to the 1,000,006. Or if you wanted that in kilojoules, knock 3 off of the 6 and 2.53 times 10 to the third. Kilojoules. Anyways, the point thing is here, is this reaction spontaneous? No, why? Because it's a positive number. Now, is it possible to get a negative delta G if your E standard of the cell is negative? Looking at this equation. If E standard of the cell is negative, is it possible to get a negative out of this equation? No. So under standard state conditions, that's the key there. Under standard state conditions, if you have a negative E standard of the cell, is the reaction going to be spontaneous or non-spontaneous? Non-spontaneous under standard state conditions. We can make it to be spontaneous by changing the conditions, but under standard state conditions, it's always going to be non-spontaneous. All right. There's our answer, non-spontaneous. All right. So we can also use this to determine K. What is K again? Equilibrium constant, all the way back to chapter 15, the equilibrium constant. So we're still on page 892. They're looking at the equations. If we take the equation and we just use this delta G is equal to negative NF E standard of the cell, and we know from chapter 18 that delta G standard is related to K using this equation, delta G standard is equal to negative RT natural log of K. Plug those in, we can end up with this equation here. E standard of the cell is equal to 0.0592 volts divided by N, again, N is still our number of electrons, times the log of K at standard state conditions, so 25 degrees Celsius. So this is equation 19.5. So we can use this to calculate the equilibrium constant. So delta G again tells us it's spontaneous. What kind of information can K, the equilibrium constant, tell us? If a K is really, really small, what does that tell us about our reaction? That it mostly goes forwards or mostly goes backwards? If K is really, really small, does it mostly go forwards or mostly go backwards? Or mostly products at the end or mostly reactants at the end? Reactants, mostly reactants at the end. So if K is really small, then the reaction favors the reverse reaction. Whereas if K is really, really big, then it's going to favor the forward reaction. So let's try this out. Calculate the equilibrium constant, K, for the following reaction at 25 degrees Celsius. Solid tin plus 2 copper 2 plus ions is in equilibrium with tin 2 plus aqueous and 2 copper ions. So again, I would have only given you the top reaction, but you can determine what was oxidized and what was reduced from the top reaction. If tin goes from no charge to 2 plus, is that gaining or losing electrons? It's losing electrons, therefore that is our
Oxidation.
oxidation. Good. So if that's our oxidation, is that our cathode or anode? Anode. Good. Meanwhile, copper goes from 2 plus to not no charge, but 1 plus. That's still a reduction, but I did not reduce all the way down to copper with no charge. Why am I saying careful? Because when you look at the table, 19.1, it's really tempting to go with the first copper ion you see, but that may be the copper 2 plus reduction all the way down to copper with no charge. So make sure when you're looking it up, you look up the copper that goes down to that is reduced by just 1 electron. All right. So the copper, that's our reduction, therefore that is our cathode. So the copper 2 plus to copper plus from the table is 0.15 volts. Again, be careful you're not grabbing the first one you see. Make sure it's the one that goes down to +1, not down to no charge. Well, tin is negative 0.14 volts. So let's go ahead and calculate E standard of the cell. So E standard of the cell, cathode minus anode. So it'll be what minus what? Good, the copper minus the tin. So the 0.15 minus the negative 0.14 volts. And that gives us what? Good. Positive 0.29. So remember our equation that contains K here says E standard of the cell is equal to 0.0592 volts over N times log K. If we want to solve this for K, let's go ahead and just off to the side there, solve it for K. So first we're going to move this fraction to the other side. If you move the fraction to the other side, what happens to it? It flips. Good. So we end up with N on the top, and that's 0.0592 on the bottom. Man, come on, cut that out. Then E standard of the cell, and all of that is equal to log of K. Now, how do we get rid of the log? Good, 10 to the power. So 10 to the power of all of this will give you just K. All right. So over here, color here, 10 raised to the E standard cell times N. Now what is N going to be for this reaction? 2. Good, 2 electrons. So N times E standard cell is 2 electrons times the 0.29 volts. Man, all divided by, you know what? I'm just going to show you. There. 10 to the N E standard divided by the 0.0592. So there's the 2 electrons there. There's the E standard cell we just found, divided by the 0.0592 volts. So make sure all of this is inside of the power of 10. And you should get 6 times 10 to the 9th as our K. So K very big, therefore the reaction goes mostly forward and you end up with mostly products. Which our E standard cell here was positive. So if the E standard cell is positive, then the reaction is what? Spontaneous or non-spontaneous? If E standard is positive, then the reaction is spontaneous at standard state conditions. All right. Ready to move on to the next section? Any questions about how to calculate delta G or K from a standard cell? All right, so I keep on giving that disclaimer under standard state conditions. So the next section we're going to say, well, what if you're not in standard state conditions? The spontaneity of redox reactions under conditions other than standard state conditions. So the first thing we're going to talk about is something called the Nernst equation. Nernst equation. So if we consider a redox reaction, just a simple A plus B goes to C plus D, and delta G non-standard is equal to delta G standard plus RT natural log of Q. Q, again, is the reaction quotient. So concentration of products over concentration of reactants. We can simplify this down to this equation here that says that E standard is equal, or sorry, E is equal to E standard minus RT over NF natural log of Q, which we can then further simplify as E standard minus 0.0257 volts over N for a natural log versus that same 0.0592 if you're LOG log. The only difference is whether or not you're hitting the log button or the natural log button on your calculator. Both equations work exactly the same thing. It's just going to change what the value of the constant is there. And we are on. Yep, one or the other. It basically boils down to whether or not you prefer to use the log button or the natural log button. Q is the reaction quotient, so concentration of products over concentration of reactants. Usually, I'm going to stick with the log one instead of the natural log because the constant in it is the same as the constant in the last equation we used, so fewer constants to remember, 0.0592 volts. And that is equation 19.7 on page 895. So let's look at this in terms of an equation. Now, remember, in standard states, what was the concentration of all ions? 1 molar. So Q at standard state would just be what? Standard state, if everything is 1 molar, what does Q end up being? If Q is the products over reactants? Just 1. What's the log of 1? 0, which means that whole second term here would go away, and E is just equal to E standard, right? So that is where this idea is coming from. If you are already 1 molar, you're already in standard state, so your E is E standard. So what if you're not 1 molar is what we're going to look at. So in this next reaction, or in this next problem, we are not 1 molar. Predict whether or not, using delta G, the following reaction will occur spontaneously as written at 298 Kelvin. Solid cobalt plus iron 2 plus goes to cobalt 2 plus iron, assuming rather than 1 molar of each, cobalt 2 plus is 0.15 molar and iron 2 plus is 0.68 molar. So let's first of all calculate what Q is. So Q is the reaction quotient, which means it is the products over reactants. either their concentrations or their pressures of their gases. So in this case, which one is going to be the product that goes on top? Good, CO2 plus, so concentration of CO2 plus. And then we can ignore iron solid because solids don't belong in reaction quotient. What goes in the bottom? Good, Fe2 plus goes in the bottom. 2 plus goes in the bottom. And then we ignore cobalt solid because, again, solids don't appear in the reaction quotient. Plug in the numbers we got. 0.15 molar over 0.68 molar. And what is the value of Q? Good, 0.22. So that is our Q that we're going to use in our Nernst equation. The other thing we need for the Nernst equation is E standard of the cell. So E standard of the cell is cathode minus anode. So in this case, which one is going to be our cathode, the iron or the cobalt? Iron. Iron's getting reduced, so iron is our cathode. So we need to look up the value in the table of iron, iron 2 plus. Go ahead and do it for you. Iron, iron 2 plus is negative 0.44. I'll write it here. E standard of the cell will be equal to E standard of the cathode, which in this case is going to be the iron slash iron 2 plus, minus the anode, which in this case is going to be cobalt, cobalt 2 plus. All right. Looking up from that table, iron, iron 2 plus is negative 0.44 volts. And cobalt, cobalt 2 plus is negative 0.28. It was being so good for a little bit there. Negative, what did I say? 48? 28. So what do we get for E standard of the cell? Good, negative 0.16 volts. So now we have E standard of the cell and we have Q. So we have everything we need to plug in to the Nernst equation. E standard, what is N going to be on the bottom here? 2, good, because 2 electrons were transferred in this reaction. So N is going to be 2, and then log of the Q that we found. So E standard of the cell we found to be negative 0.16 volts, 2 electrons, and then we found Q to be 0.22. We end up with a E of negative 0.14 volts. Now, if E is negative, can the reaction be spontaneous? No, because if you plug that into the equation from the last section, if you have a negative E, then G will always be positive, and positive G ends up being non-spontaneous. So this tells us that the reaction is non-spontaneous. So even though this reaction may have been spontaneous at other concentrations, it's not spontaneous at the concentrations that they gave us. Questions? Now here's a question. In a redox reaction, if I had put, say, copper with copper nitrate on the inside and copper with copper nitrate on the outside, would there be any sort of potential difference between them? If they're both copper? No, if they're both copper, there's no potential difference between them. unless I change the concentrations, because as you can see, changing the concentrations changes E. If I change the concentrations and have a big enough difference in the concentrations of those two solutions, then I can actually get a redox reaction running through them. This is called a concentration cell. A concentration cell has the same ion on both sides of the cell, but at different enough concentrations that you can get electrons flowing across them and end up with a potential difference. It's not going to be huge, but it can be measurable. So same material, just different ion concentrations. Concentration cell. So for example, let's look at these two zincs. So here I have zinc on the right is going to be 1 molar. Zinc on the left is 0.1 molar, or 10 times more dilute than the zinc in the other cell. If I measure the potential difference across this in voltage, I get 0.0296 volts. Not a huge difference, but still measurable, and as we're about to see, something we can actually calculate what will be the potential difference across a concentration cell. So we can still use the Nernst equation for this. It's just in that case, E standard, if they're the same, is going to be 0. Right? Back at the Nernst equation real quick.
You're probably going to answer this, but is the one with the less concentration always the anode?
The one with less concentration ends up being the, yeah.
Okay.
Yeah. Mm-hmm. Because it flows from high concentration to low concentration. All right, so in the Nernst equation, if they are the same, they're both zinc, they're both iron. If they're the same identity, then E standard is going to be 0 because those would be the same numbers. So then the Nernst equation just becomes the second half, where Q is products over reactants, and the anode is going to be the oxidation, which is going to be the less concentrated one. We're going to go back to this. Yeah. All right. So looking at that overall reaction, if our oxidation is the one that is less concentrated and our reduction is the one that is more concentrated, so the 1 molar versus the 0.1 molar, then we get that the overall reaction is zinc going from high concentration towards the zinc that's low concentration. Again, E standard goes to 0 because they're the same thing. 2 electrons were transferred in this reaction. So we have the concentration of Z dilute, because the product, as we can see here, is going to be the ion that was produced in the oxidation, which is our anode, which is the less concentrated one, over the more concentrated. So if you don't want to try and keep track of the whole train of thought, which one is going to be oxidized, which one therefore is the anode, therefore which one goes on top of the Q, you can just rewrite the Nernst equation for a concentration cell as getting rid of the E standard and saying the log of the dilute over the concentrated. So for a concentration cell where they are the same ion, it's always going to be the dilute over the concentrated will be your Q. All right. So we're going to take a step back real quick and talk about something we learned about back in Chapter 17. Back in Chapter 17, we were learning about KSP, or the solubility product constant. So way back in Chapter 4, we had the solubility rules that said if you are this combination of ions, you are not soluble. And then in Chapter 17, we said, well, they're technically soluble in a very, very tiny amount. And some of those KSPs were really tiny, like 10 to the negative 20 something, 10 to the negative 40 something. And you're like, how on earth could you measure a concentration that low? Well, here's one way we can measure it. We can measure it by measuring the cell potential of the ions. So we have one, in this case, we're trying to find the KSP of silver cyanide. We can do this by finding what the concentration of silver ion is in a silver cyanide solution that's completely concentrated, meaning you mix silver cyanide in there until nothing dissolved. For something that generally is considered insoluble like silver cyanide, it's not going to take very much. And then you compare it to a solution of known concentration of silver. So in this case, we're going to use silver nitrate. Silver nitrate, very water soluble, but it also produces silver ions. So what we're really doing here is comparing the silver ions in the silver cyanide versus the silver nitrate. Cyanide and nitrate are just going to be our spectators. We're going to ignore them. We know that we have made our silver nitrate solution to be 1 molar. And then the silver cyanide, we don't know what its concentration is. That's what we're looking for. What is the concentration of the unknown? We measure the cell potential across this concentration cell and find it to be 0.47 volts. The question is determine the concentration of the silver ion, and then from that calculate the value of KSP for silver cyanide. All right. So in our Nernst equation here, well, we'll use this version of the Nernst equation here. What we're looking for is what is the silver ion in the dilute solution. We have measured what E is. We know that in the concentrated solution, the silver nitrate is 1 molar. We're going to determine, therefore, what is the concentration in the more dilute or the silver cyanide solution. Go ahead and just open up a second extra page here. Give us some space to work. New slide. All right. So, silver. What is the charge on a silver ion? Ag what? Yes, it's a transition metal, but it's one of the transition metals with only one possible charge. It's not 2 plus, it's just 1 plus. So silver 1 plus. Why is it important to know that? To know N. If I'm going to silver 1 plus, what's N going to be here? Just 1. Just 1 electron is going to be transferred. So let's look at, give me some space here. Next page. There we go. So the Nernst equation, E is going to be equal to E standard, which for a concentration cell is going down to 0. And then what's the rest of it? Negative or plus? Negative 0.0592 volts over 1 electron is equal to, or sorry, not equal to, times what? Of Q, where Q is going to be what over what? Good. Dilute over concentrated. Come on, stop doing that. Dilute, which is what we don't know, over concentrated. What was the concentration of the concentrated silver? 1. Good. 1 molar. So that's going to be 1 on the bottom. And we measured the E for this to be 0.470 volts. So that's all going to be equal to 0.470. So at this point, we need to solve for E, or solve for X. Bring this to the other side. Log of x over 1. I'll just put log of x because dividing by 1 is just nothing. So log of x is equal to that 0.470 divided by the negative 0.0592, which gives us negative 7.94. Now what do we do next to get rid of that log? 10. 10 to both sides. And we get that x is equal to what? Good. Man, -8. So if that is our x, that is the concentration of silver ions in silver cyanide. So we still need to find KSP. So silver cyanide, AgCN. KSP is the K or equilibrium constant for this dissolving in water. So if this is my solid, what would my products look like for this dissolving in water? I'll get two products. What are they? What'd you say? H? There's no H there.
It would just be AG.
AG.
Cyanide.
So Ag with what charge? Plus, and then that's aqueous. And then what's the second product? CN with what charge? Minus. And that's also aqueous. So that's the cyanate ion. All right. So if I were to write the K for this reaction, the equilibrium expression, it's products over reactants. So my products are silver and cyanate. Anything go on the bottom? No, because my reactant is a solid, so I ignore it. Now I know what Ag is, but what about Cn? Can I determine what Cn is? I can use stoichiometry. What's the ratio between silver and cyanide here? 1 to 1, which means that if silver is 1.15 times 10 to the 8, then cyanate is also 1.15 times 10 to the negative 8. So K is just going to be equal to that 1.15 times 10 to the negative 8 squared, because you're multiplying it by itself. So that gives us KSP of what? SP. Good. 2 times 10 to the negative 16. How do you feel about that? Any questions? Ready to step away from the math for a little bit? All right, let's take one section break away from math. So the next section we're going to talk about is batteries. Now, in this section, although I will be showing you a lot of the reactions, I'm only going to want you to know the difference between these kinds of batteries. I'm not going to ask you to, on a test, write out the equation for any of these batteries or without other given information, or calculate the potential across these batteries. Just recognize what is the difference between a lead storage battery and a fuel cell battery. So just being able to recognize these different types of batteries. So I said that a galvanic cell earlier works the same idea as a battery because it can store potential energy there. but it's not very convenient to have this whole setup with all these liquids splashing around in our flashlights, right? So the same reaction is going to be going on inside of batteries. We're just going to try and find some way to have it more portable, smaller, and easier to fit around. So let's look at something called a dry cell battery or alkaline battery. So these are your copper top Duracell, Energizer type batteries. It's still the same idea. You're still having a redox reaction, but although it's called dry, there still has to be some moisture because you can only have redox reactions in aqueous solution. So generally what happens inside of this is you have some sort of a moist paste. That moist paste allows there to be ions dissolved in aqueous solution just enough to have the electrons being able to transfer. So it's called dry cell because there's no actual fluid, but there is technically moisture in there, which means when batteries go bad, they corrode and they tend to leak. That stuff coming out is the moisture from inside the battery. So although it's called dry cell, it is still technically moist on the inside. So that enables us to have it self-contained like that. So for this particular one, we have in the moist paste, we have zinc chloride and ammonium chloride, and then we have a layer of magnesium oxide. In the very center core of this is a graphite cathode. So a graphite cathode basically looks like a giant piece of pencil lead. This is a graphite cathode right here that I just broke in half at the beginning of class accidentally. So graphite is carbon, and we use them because they tend to have very high potentials. They tend not to corrode, so it's a good cathode. It tends not to corrode. In this case, we have a zinc anode, and that's the outer part that touches the connectors inside of whatever device we're trying to power up, like the flashlight. So if we look at the reactions here, at the anode, we have that zinc anode. At the cathode, we have the reactions going on in that moist medium. So that's the ammonium from the ammonium chloride, the manganese oxide, which separates it from the graphite core there. And we have the two different reactions going on here. Now, these are also called alkaline batteries. In the very beginning of chapter 19, we learned about balancing redox reactions, and it was important whether or not your reaction was an acidic solution or basic solution, because the very end of the basic solution reactions, we had to add in hydroxide to cancel out those hydrogen ions from the acid that we got when we balanced these reactions. Now, we call these batteries usually alkaline batteries because that paste is alkaline or basic. So we're going to have the hydroxide in there. Again, I'm not going to ask you to balance these reactions. These are just examples. Just be able to identify the difference between a dry cell battery and other batteries. So next one, lead storage battery. What's the most common thing we use lead storage batteries for? Car, right? Looks like a car battery. It is a car battery. So a lead storage battery has lead gills that are down in a solution of very, very concentrated sulfuric acid electrolyte solution, which is why if your car battery is leaking, should you grab it with your bare hand? Now that's concentrated sulfuric acid, very, very bad. Sometimes when a car battery goes bad, it's because that sulfuric acid has leaked out or has dried up, and it's dry on the inside of the battery. And if you really just need to get to a destination, sometimes people will pour a little bit of water inside of the cap just to get the reaction going again. Short-term solution. Overall, it will eventually ruin your battery, but at least gets you where you're going, so hopefully you can get a battery. So, but the same thing happens here. We have lead in these gills here, and lead oxide. And then we have the electrolyte solution. So the overall reaction going on here is the lead is getting oxidized. That's our anode. Our cathode then are going to be the gills of lead oxide reacting. And the sulfuric acid is going to be our electrolyte solution that facilitates all of this. Now, unlike most alkaline batteries, this is rechargeable because just the charge within one battery on your car is not going to last you very long, because cars, at least fuel cars, not electric cars, don't run off of the battery. They run off of what? Fuel. So really, the purpose of the battery is just to start the car. That's all you need the battery for. It starts the car. That's all it does. After the car is started, then it's the fuel that keeps the car running. And while that car is running, it is recharging this battery through the alternator, which is why if your alternator goes bad, as I have learned several times, because that is like the most common thing to go bad on my cars, if the alternator goes bad, your battery doesn't get recharged, and you think your battery's bad, but it's actually the alternator. So the alternator is what is going to, when the car is running off of the fuel, run this reaction in reverse, so the non-spontaneous reaction, run it in reverse and recharge it. So we also have lithium-ion batteries. What do we use lithium-ion batteries for? Cell phones, right? So lithium-ion batteries are also rechargeable like the lead storage batteries, but they are much smaller, more contained, generally safer, except for when they explode. But in most cases, they're a lot safer and easier to handle and carry around in a cell phone than a lead storage battery. So in that case, our anode is the lithium, and then your cathode is going to be the lithium ion, and usually something like cobalt oxide here. Now, the cool thing about this is if you look at the difference in these, the cell potential ends up being 3.4 volts, which is a rather large potential difference for such a small thing, which is why it's such a great battery for things that we want to make small, like cell phones. We keep on wanting to make them smaller and smaller and smaller, or smartwatches and stuff like that, because we can make these things very, very small, but still have them be able to have a lot of energy and make them rechargeable, so you can plug in your cell phone and recharge it overnight. Fuel cells. So fuel cells generate the electricity through, as the name would apply, fuel. In this particular example, we have methane as our fuel. So in this case, this is probably the least efficient of these. This is not something you would find in a battery you would just plug in your home. This is more used for large industrial operation type things. To generate electricity, the reaction here, and this is combustion, so we're burning it. So we combust something, burn some sort of fuel source. This is then used to heat water. That water vaporizes and turns into steam. Those steams then drive a turbine. Spinning that turbine then is what generates the electricity. So this is very inefficient because a huge amount of the energy produced in this is just lost to the environment, just lost to heat. In each step, you're going to lose a lot of energy. So these are relatively inefficient, but they're also relatively cheap because most of the time fuel is easier to come by than things like lithium. So you can also have a fuel cell, a galvanic cell that requires continuous supply of reactants. Now, unlike the other ones that are more self-contained, in a fuel cell you have to keep on pumping in the reactants to keep this thing going. So let's look at a simple fuel cell here. So here we have a simple fuel cell running a motor, and here in this case we've got potassium hydroxide, so this is happening in a basic solution. The fuel that we're pumping in here is hydrogen gas and oxygen gas to continue to complete the combustion. And so the combustion occurs in the solution and it drives the motor. These are probably the least common ones that you come across. Again, they're not incredibly efficient, and you have to continuously keep on pumping hydrogen gas and oxygen gas into them, which aren't really things you generally would find easily. All right, and there's the overall reaction for that one. All right, so those are the different kinds of batteries. Questions? All right. So next thing we're going to talk about, going a little bit back to the math, and then the last section won't have any math, I promise, is electrolysis. So What happens if the reaction is non-spontaneous, but you really need the reaction to run? If I really need this reaction to run, but it's a non-spontaneous reaction, non-spontaneous just means it doesn't run under those conditions. You can change the conditions, or you can force the reaction to run in reverse by pumping it full of energy, usually doing that by pumping it full of electricity. So a galvanic cell runs through a spontaneous reaction. It is self-contained. It is what generates the energy. An electrolytic cell is the opposite. An electrolytic cell, on the other hand, is usually a non-spontaneous reaction, and it usually consumes energy to run its reaction rather than providing it. So galvanic cells provide energy while electrolytic cells consume energy. So let's consider the electrolysis of molten sodium chloride. So sodium chloride, salt, right? Table salt. Say I want to make pure sodium. How would I make that? So sodium, 1A metal, extremely reactive. It's an alkaline metal. It is not an alkali earth metal, which means we can't just mine pure sodium out of the earth. If you mine sodium out of the earth, it's in the form of salt, generally sodium chloride. So how on earth do we have pure sodium? We produce it through electrolysis. So the first step in this electrolysis, we're going to take sodium chloride and we're going to heat it up until it's molten, so it's liquid. Once it's liquid, then we can have a redox reaction occur where we take the chloride ion in the sodium chloride, we oxidize it so it loses electrons so that it ends up being chlorine with no charge. That's a gas. Get that gas out of there fast, because chlorine gas, is that something you want to breathe? No, so this is not something you should do at home because it produces chlorine gas. Meanwhile, the sodium is going to be reduced from sodium ion, gains electrons back, to just pure liquid sodium. That pure liquid sodium then we can cool down and then end up with just the sodium in a solid state once we very slowly cool it down. So this image is on page 904, shows how this would be done in an industrial operation here. So we have the molten sodium chloride, so we take salt, we heat it up to a very, very high temperature here. And then the cathode and anode has electricity running through it. This electricity runs through it, causes the electrolytic cell to start running that non-spontaneous redox reaction. The chlorine gas we pump out of there and dispose of safely or use it for other industrial operations. And what is left over is liquid sodium. This liquid sodium we can then pull out, cool down, and have pure solid sodium. So a couple of semesters ago, we used to offer chemistry classes over in the Workforce Development Center down in Clayton. So we had a full chemistry lab over there, and we offered a lot of chemistry classes over there. That was mostly due to the bioprocessing program over there, which they minimized that, reduced the number of chemistry classes required for it, and because there's fewer students, they just shipped them over here to take classes on our campus. And so we had to shut down the chemistry lab over there. So part of that involved myself, and at the time there were 2 of us, chemistry instructors, going over there and just taking anything we could possibly use out of that chemistry lab and bring them back here. So a lot of that was materials that we had never seen before because they were just sitting back there in cabinets used by instructors who were no longer here at JCC. And we didn't know the story behind some of them. And one of them we found back in the cabinet was this, looked like a big old soup can, about that big, and it just said sodium on it. Well, when you purchase sodium, generally it comes in a big can, and inside of that can is some sort of extremely absorbent material, looks like kitty litter, and inside of that kitty litter is a smaller jar, glass jar, full of oil with the solid sodium inside. That way there's no way for moisture to get into the sodium. So that's what we assumed, that inside this jar was that setup, since that's how it's generally done. So we brought it over here, we left it in the cabinet and wasn't really thinking about it very much. Then I came in one day to use the lab, and the other chemistry instructor was kind of like panicking, and he was over in one of the fume hoods, and he decided to open the can with a can opener because it was just a sealed can. And when he opened the can with a can opener, it was pure solid sodium inside, which was, as soon as he opened the can opener, exposed to air and the moisture in the air. And so he was working as fast as he could, trying to scrape all the sodium, which was, sodium is a pretty soft metal. It's not like a solid. This is the kind of thing you can cut with a butter knife. He was trying to scrape it all out of that can and get it under oil as fast as possible. So we were scrambling, trying to get all the solid sodium scraped out of the can, put it under oil, and we didn't have much oil. We had some baby oil, so that's what basically we were using to try and get this. Luckily, there was no incident, and we got it all under. But that is one way, apparently, that they can package this thing. They pull out the liquid sodium here, pour it into a can, let it cool in the can, and sell it to unwitting customers here. But you can also technically do this in a smaller setup here, molten sodium chloride, cathode and anode. The problem here is that the chlorine gas will come straight up as a vapor, so you would definitely want to do this like in a fume hood or something like that. I have a student who is currently doing an honors project with me, and part of his honors project is trying to make solid sodium. Now, we found that sodium chloride molten was too hot to really get this to work, but we did get this to work with, instead of sodium chloride, sodium hydroxide. So he took sodium hydroxide pellets, he melted them down, still probably set up over here, here it is. Melted down the sodium hydroxide in here, put in a cathode and anode, hooked up to voltage here, and we were able to produce a very small amount of pure sodium metal there that way. So, kind of neat reaction. So, in lab tomorrow, we are going to make our own galvanic cells. We're also going to finish up the chapter 19 lecture, so make sure you do bring your calculator and notes so we can finish up the chapter 19 lecture.